Good evening, everyone. It's 6 o'clock on December the 15th. This is our last ACM Chicago meetup, webinar, whatever you want to call it, for this year. So thank you for coming and supporting us for this year. So we are very glad to have Dean Wampler from Domino Data Lab that will be talking about reinforcement learning with Ray RLlib. And just going through some introductions before we start. So we also have a joint, this ACM Chicago meetup is also joint with IEEE Computer Society Chicago, which we've done throughout the past kind of 2 years or so. So we do the same topics on software, hardware, AI, big data, cloud computing, cybersecurity. So I'm also the chair of this Computer Society Chicago. Here are the information if you want to know more about Computer Society Chicago, our web, Facebook, Twitter, LinkedIn. We also have a YouTube channel. And if you want to become a society member, the URL is there. Just a bit of housekeeping notes on this. These slides are going to be sent to you after the webinar, and a copy of the recording will also be sent to you as well. And if you need a professional development hour for your PN, we will provide that too as well. So we also want to thank members of the Mid-America Club IT Connect group that also have joined us from the past 2 years of meetings that we've had. We have VJ who's on the line. He is the chair of Mid-America IT Connect Club. So Mid-America Club, if you're not familiar, it's a private business club on the 80th floor of the Aon building. Has a really, really nice view of the Chicago skyline. And we've actually had previous talks when we were in person, actually in Mid-America Club. And so, whether it's Loyola or whether we have it at Mid-America, hopefully when we do become in person, we can kind of continue that. And of course, ACM Chicago, this is the main meetup. So for those who may not be familiar, we are the Chicago chapter of the Association for Computer Machinery. That's what ACM stands for. So I am the chair. We have Mark Temkin, who is our vice chair. Yep, he has his hand there. And also Greg Newmark, who is the treasurer. There you go. Thank you, Greg. And we have also our stuff on the web, Meetup, Facebook. I'm sure a lot of you people know about this meetup because we advertise it on the meetup group. We have a Facebook channel. We have Twitter, LinkedIn. We also have our YouTube channel. So please subscribe to our YouTube channel so you can be able to see our previous events that have been recorded as well. And the one for tonight will also be posted there. And of course, if you want to get the benefits of ACM membership, you can go to acm.org/membership. Real reason why you're here today to attend the meetup webinar is that we have our speaker, Dean Wampler. I'm going to ask our Vice Chair, Mark Temkin, to give an introduction to Dean. So Mark, take it away.
Dean Wampler's been a previous speaker of ours 10 years ago. I certainly, when I was thinking of who could be our next speaker, he came to mind right away because I know he always had numerous interesting topics. Dean has been a prolific author. Some of you may be aware he has a popular book on Scala, programming Scala from O'Reilly Press, certainly a well-known publisher. And so I know that this is going to be a great presentation on reinforcement learning. So let's welcome Dean Wampler.
Thanks for having me. Let me share my screen. There we go. Get set up here. By the way, programming Scala is an amazing Christmas gift. If you're looking for that special gift for that special someone, just saying. So anyway, this is about reinforcement learning. I've been interested in this topic for a while. I have kind of an interesting story about that. I actually worked for a company called Anyscale for a while before Domino, and Anyscale was spun out of Berkeley, where they created this distributed Python framework called Ray that I'll introduce briefly. And on top of that is this, I think, state-of-the-art library called RLlib. So it's a great way to actually learn and use reinforcement learning. I'm actually going to demo it. The demo is actually from the training materials that I helped write while I was at Anyscale. So I'll give you the link for that. and you can just go download that stuff and play with it. And, you know, hopefully, if you really want to kind of like learn by doing, it's one way to do it. And if you find that training too wordy, you can blame me for that. It's probably a little too wordy. Just a bit about the links here. I welcome emails and Twitter posts if you want to follow up. Ray.io is the place to start for all things about Ray, including reinforcement learning. And you can find the slides already at actually a longer version of the slides at deanwampler.com/talks, which will redirect to another URL, but nevertheless. And I'll also give the slides to the team here so that you can get them that way as well. Okay, so I'll briefly talk about why Ray, why it was built, and was, you know, and why it's kind of a great library. So if you're doing distributed Python, whether or not you're doing anything with data science, I definitely recommend checking out Ray as a tool to make it a lot easier. And that's what got me interested in it in the first place. You know, I'll spend most of my time talking about what reinforcement learning is all about, and just, you know, give you kind of a teaser for some of the core concepts. And we'll actually play with the Ray RLlib example. Actually, I'm not going to do the last two steps here, or bullet points. I cut those out of the slides for time's sake. The longer version of these slides has those two, or covers those two topics. So if you're interested. All right, first, why Ray? It kind of emerged out of a couple of trends that have kind of been very characteristic of our industry. One of which is like the amount of compute required to do things like training neural networks. You know, it's just been way outstripping Moore's law. You know, notice the number of petaflops per day for training some of these massive models, and these numbers are actually already obsolete. You know, way outstripping Moore's law. So it's made it necessary to go distributed in order to actually do kind of like model training, so-called hyperparameter tuning, and so forth, in any sort of reasonable, you know, a human clock time. You have to do it distributed. At the same time, Python has been growing enormously lately, in part driven by interest in ML and AI. You know, there's other languages that people use. I happen to like Julia a lot, even though it's still kind of a dark horse, obscure language by comparison. You may use some other languages out there, but Python has become kind of the de facto language for ML and AI and so forth. So that kind of has driven the need to have, you know, a really good way to do distributed Python. There are some tools that are focused on data science for distributed computation, like Dask, if you know much about the Python world. Ray was actually built by researchers at Berkeley to solve kind of this pressing need for the kind of research they were doing, where they needed to do cluster-wide you know, compute for model training and experiments. And then they realized that this was actually a very general purpose, flexible, distributed framework for any kind of Python programming, not just machine learning use cases. But if if we go back to the machine learning landscape, you know, roughly these are kind of the stages of grief or whatever that you go through when you're doing you know, model development and serving today. You know, there's like getting your initial data in, that kind of ETL. We've done it many different ways over the decades, and you know, I'm just listing some of the tools that people use for these things. You may do stream processing. Hyperparameter tuning is where you figure out the model structure that's optimal. That's a non-trivial problem for neural networks, where there's all kinds of ways you can architect a neural network. And once you've decided on those hyperparameters, then you might do the final training with real data to, you know, come up with the model that you deploy to production. A big part of that when you're doing reinforcement learning is the need to simulate like environments that you're targeting, as we'll see. And then you know, you're going to serve it in some capacity. And this slide really needs to be updated. A lot of these icons have changed quite a bit, in fact. But getting back to Ray, so the realization was that a lot of this stuff really needs distribution, concurrency, all that kind of good stuff. And it would be great to have a common core framework that could give you that kind of, you know, fundamental building blocks for distributed computing, and then layer on top of that domain-specific libraries targeted at particular parts of this pipeline. We're going to talk about RLlib today. That's the reinforcement learning library. The icon will make a little bit more sense when I show you the example. That little sort of upside down looking T is actually a so-called cart pole, which is sort of the hello world of reinforcement learning. There's everything from a model serving library called Ray Serve. Ray SGD is specifically focused on stochastic gradient descent. acceleration. And then RayTune is this nice library for doing hyperparameter tuning. But we're going to focus today just on the RLlib. But you have these other libraries that you can pull on. And there's a lot of third-party libraries now. So for example, if you're working in the natural language processing space, libraries like Hugging Face and Spacey are now building on top of Ray to enable easier distribution. Michelangelo was like a experiment tracking kind of hyperparameter tuning sort of system out of Uber. That's actually being productized. I forget the name of the company, but it's also using Ray. So you're starting to see Ray appear in a lot of these, especially these sort of data science related systems. So just very quickly, and I'm doing this because it's such a concise API, and it's really, I think, the most elegant way to do sort of like this. What's the simplest way I could do distributed computing without a lot of like knobs and so forth that I have to get right in order for it to just work? I think Ray really nails this. And so I think it's worth taking a few minutes to walk through this just quickly with a basic example. So let's suppose that we have these two Python functions, one of which is going to construct some sort of NumPy array. NumPy is a popular library for working with like arrays of floats and so forth in Python. Don't care about the details. We're just going to return this array. And then we're going to have this other Python function that adds to arrays. So this is stuff that you already know if you work with Python at all today. And now we want to make this a distributed application because we're going to add a lot of arrays and they're big and so forth. So the first thing we do is we just adorn these methods with this ray.remote decorator, and that turns them into remote tasks. And for completeness, there's some imports that you have to add, and you have to initialize Ray, and there's a lot of details there that we won't get into, but it's pretty basic actually to write your app to get started. And then whenever you call these functions, you call them, instead of saying make array with an argument list, it's now make array.remote. Python is malleable. They could have instrumented it in such a way that you don't have to have these remote calls, but I think it's good that they did it this way because it's a reminder when you're reading the code that you're actually making it this sort of remote asynchronous method call and not doing something that's just in process in the usual Python way. So we're going to make a couple of arrays, and what it returns is basically a future that we can then use to get the result once it's finished computing somewhere in our cluster. And then we can call this add arrays by passing the two references to from the other two, and then do the addition that we want. So a pretty simple example, but there's some cool stuff going on here that makes our jobs a lot easier. And then finally, when when we're ready to get a value, we use ray.get to wait until it's done and then fetch the value back and so forth. But one of the cool things Ray does automatically is because there's a dependency for add arrays on the results of the first two calls, Ray automatically does that sequencing for us. We don't have to have like some sort of wait logic and poll logic or any of that stuff. It just kind of does it for us, which is pretty great. And all of this is running asynchronously, so we can go on and do other things while we're waiting. And the other thing too, if you're paying attention, is that this add arrays took basically two NumPy arrays as arguments. But when I'm actually calling it, I'm passing it these reference objects. Ray will automatically do the wait until those available, extract the actual values using ray.get internally, and then pass the actual arrays to this call. So once again, a lot of boilerplate I don't have to write, it just works. So that's sort of the gist of doing basically cluster-wide distributed computing with Ray. It feels very much like synchronous programming in a lot of ways, but it's actually doing a lot of heavy lifting behind the scenes. Now, sometimes we need state, though. The ones on the left are kind of stateless computations. Well, here they just leverage something we already know for managing state, which is classes, for object-oriented programmers. So here we're going to take just a regular Python class that basically has an internal counter. Every time I call increment, it's going to increment its value, and then it'll return that value so that, it could be like an indexer or something for a database, something or other. And here, once again, ray.remote is how we turn this into an actor. I won't go into the actor model. If you've heard of it, then you kind of know what's going on. If you haven't, it's just sort of a fancy message passing system that manages thread safety and running these methods and so forth. Oh, and one other thing we had to add is with actors, you can't just read the members, the member values of this class, the value member. You have to actually have a getter to get it. So I added that method to actually retrieve the value if I don't want to call increment to get it, and so forth. But otherwise, it looks just like a regular Python class. And then we call it kind of the same way. We construct it with .remote. We call the increment method with .remote. And what happens now is when I call ray.get, passing it an array of the two elements, of the two references, then I'll get the return values 1 and 2. So, again, a pretty simple way of managing distributed state. You can see this is very fine-grained. It's really nice for complexity that's really at a very small grain level, but it could also be used for large-scale stuff. So, for example, if you were going to rebuild Apache Spark purely in Python, Spark has a particular compute model. It does a lot of stuff under the hood for distributed computation. You could easily build it on top of Ray using these primitives, and you could make them as coarse-grained or fine-grained as you want. It'd make it a lot easier to add more than just kind of the MapReduce model that Spark uses. You could add other kinds of models for computation. Okay, anyway, that's kind of a teaser for what Ray is all about. Hopefully you can appreciate the elegance and concision of it, especially if you've used other distributed concurrent programming toolkits. It's pretty great for this. So now let's get into reinforcement learning. And first, motivate why it's interesting. Okay, so the elevator pitch about reinforcement learning is that you have some agent interacting with an environment. The agent is observing the state of the environment, and for whatever action it has taken in the past, it has remembered the rewards that it received after each step. Like it didn't bump into a wall, or it picked up some magic thing if it's a game, and I'm picking up weapons or whatever. And so it keeps track of these rewards. And based on these observations, it's going to make a decision about what action to take next. Now, when this thing starts, the agent probably has no idea what to do, so it will just randomly pick some action, some of which will be bad, some of which will be good. But when you play it over and over again, these so-called epics where it's doing these cycles as shown here, then you're training the internals of the agent to develop a policy that will then know how to hopefully make optimal choices. The ultimate goal is to maximize your cumulative rewards over the life of this epic. So if you get a reward after each step, then hopefully those accumulate to the maximum possible rewards. As we'll see, there's some examples where you may not get any rewards during the intermediate steps. It's only whether you win or lose in the end that's the reward. But this is the basic model. And the idea with the reinforcement part is that we play this thing over and over again, and it learns to get better and better at whatever the goal is that it's trying to achieve. Okay, and so there's some very interesting examples about this. First is games, and this is where it really got famous. So if you joined before we started, I mentioned I had a little story about this. So I was reading this, you probably can't see it because of my background, but here, I was reading the first edition of this book, the sort of standard textbook on reinforcement learning by Sutton Bartow. At the time, that book had been written in 2009. This was like, I think 2013 or something. I'd heard that reinforcement learning was this sort of obscure thing that people talked about occasionally along with supervised and unsupervised machine learning, but it wasn't used that much. And then all of a sudden, DeepMind comes on the scene and shows that you can use it to achieve expert level gameplay at Atari games, like the thing on the right here. And then eventually they used it to build this AlphaGo system that was able to beat the world's best Go players. And that was really a big deal because the state space for a Go game is actually much, much bigger than the state space for chess. So this was considered something that's going to be not doable for a long time. And yet they did it, again, around, I think it was 2013 or so. And that really put reinforcement learning on the map. And I'll show it in a minute, just a little bit more detail about how it actually works. But just to finish, sort of these applications. They've also been used for robotics, autonomous vehicles, and that sort of thing. So down on the left, you're seeing a little animated GIF for an environment called OpenAI Gym. And this is an environment of simulators, in this case, like a robot, a humanoid-like thing that you want to train to both walk, to kick this red ball, and also to deal with having obstacles thrown at it. One of the big challenges in reinforcement learning is that often you have to have some good simulator that represents the environment that you're interacting with. Because if you're training a robot or, say, a chemical plant, and you want to optimize its performance using reinforcement learning, you really don't want it to do naive stuff while it's learning, because that could be a disaster. So one of the big challenges here is that you often need to write a really good simulator that's good enough to represent the problem you're trying to solve. Which reminds me, I was going to add something to the slides and I forgot to do this. AnyScale sponsors an annual Ray Summit. And I think it was the one 2 years ago where they had a talk by a team that actually built a good simulator for the America's Cup boats, specifically the hydrofoil that's under the water when these boats are sailing. And they used reinforcement learning with that model to optimize how they design the hydrofoil and how the sailors react to different conditions. And they actually won at the America's Cup. Certainly this was a contributing factor to that victory. So you can get very sophisticated, but you can imagine there was a lot of money thrown at that problem to build a model that was a really good physics simulator for this particular domain. This happens to be one of the challenges of reinforcement learning. Is if you're modeling or you're using it for something non-trivial, you often need to build a good simulator, because you can't really trust the training process to not do something destructive when it's just starting to learn. So we'll come back to that a little bit later. Industrial processes. This has been an interesting area where kind of system optimization is related, where people are looking at ways of improving the way that we model processes, like flow of materials and things like that. This is an old problem. It's been done for a long time, but reinforcement learning, because it's all about kind of sequential activity, is a good tool to apply to this. And I picked a state-of-the-art assembly line picture just to motivate this example, obviously. But actually some other successes kind of related. Google has published blog posts about how they've reduced their data center costs by optimizing HVAC system usage and power usage in their data centers. You can use it to optimize like network topologies. And I picked a state-of-the-art network topology here on the left, again, to illustrate the point. Now, one of the cool new applications, and as we're kind of moving to the right, we're getting into things that maybe are more likely the kind of stuff you might encounter in your day jobs. You're less likely to be worried about game programming as in your professional life, but you might be interested in recommendation systems and things like that, and might need to do that for the job. Recommendations and ad serving, these are been done for a while, as you know, and there's been a lot of standard mature technologies for doing this, so-called like collaborative filtering and so forth. Like when you're a Netflix customer, they kind of model what you've watched and what you've said you like. And then they model how other people interact, what they watch. And if you happen to overlap a lot in terms of preferences with someone else, and they've watched some things that you haven't, then they'll recommend those things to you to look at next, because you're more likely to find them appealing. And similarly, when you shop at Amazon and so forth. I mean, some funny examples of where this breaks down is the old joke is, you like buy a new toilet on Amazon because you like to do it yourself, and suddenly you're just offered constantly new toilets that come out, even though you only need to buy one. So it doesn't always work like it should. And this is a case where you'd like to have some sense of evolving preferences, where I don't care about toilets after I bought that one. This is a case where reinforcement learning, because of its sequential orientation, can actually help do a better job. The other thing that it helps in is if you have a massive SKU like Amazon does, catalog that is, if you have a massive set of videos like Netflix has, and a massive customer base, the actual number crunching required can be enormous. The naive approaches are basically giant matrices. Well, this is a system that tries to be a little smarter and energy or resource efficient about making recommendations, and also supporting a little bit better time evolution of these kinds of things. If you want to find out more information about this, I need to put a link in these slides, but there was a couple of good talks by a team from YouTube about how they're doing this. So if you look at Google YouTube reinforcement learning, hopefully you won't just get videos about reinforcement learning, but hopefully a video about a from engineers from YouTube talking about this. And like I said, Netflix has also been exploring this as well. So pretty cool real world applications, rethinking an old problem in this new way. And of course, finance is also a logical place where this can be applied because once again, markets are evolving during the day and over longer periods of time. So hopefully with reinforcement learning, you can develop optimal policies for navigating what the market is doing and making good decisions. And I've seen some, preliminary what people are willing to say publicly about how they've used this. Okay, anyway, that's a whole bunch of potential applications. So let's actually find out a little bit more about how it works. So let's look at the problem of playing Go as a reinforcement learning problem. This is based on a paper that was published in 2016. I think if you Google AlphaGo and Silver, you'll probably find it pretty easily. But basically, there's a neural network under the hood. This is how they were training the policy to get smarter about making moves. And if you look at that picture at the top right, in this case, the observations are the state of the board, where the stones are and what colors and that sort of thing. And the obvious actions are where to place stones next. And also there's no intermediate rewards. In this case, it was either you won or you lost in the end. So there was a lot of trying stuff, learning to recognize these common patterns through a convolutional neural network, and then optimizing that through continuous gameplay until it got really good at playing the game. And you may have read about when this happened, again, mid-decade or so, that this system was inventing moves that no one had ever thought of before. So it was kind of amazing to watch, apparently, if you were an expert Go player. Just a little bit about what's happening with the convolutional neural network here. This is common in other applications like image recognition, where these more coarse-grained convolutions are better at recognizing larger patterns. And then the smaller little nodes in the network are good at finding small patterns of recurrent stone positions and so forth. So this is sort of the gist of what they did, using a neural network to build a fairly intelligent policy, and then observing the board state. But here's an interesting thing. So the word model comes up in the context of reinforcement learning, and you'll hear about model-free versus model-based RL. The word model is a little confusing, and sometimes I use it inappropriately too, because this is not really a model of like the way the Go game works. It's actually just a fairly naive neural network that's structured in such a way that it discovers patterns, but it really has no idea what's going on. So when people talk about model-based reinforcement learning, they're also embedding models into this agent in some sense that have some awareness of the structure of the environment that they're interacting with to try to make them a little bit smarter about decision making. But a lot of times this sort of model-free approach is actually good enough. Now, again, the word model can be kind of confusing because there is, in the sense, the thing that's simulating your environment, whether it's the game of Go or a robot or whatever, that's sort of a model in its own way, but it's not quite the same thing that we're talking about when we say model-based versus model-free. Mostly people tend to use model-free because it works in a lot of circumstances. Okay, so let's talk about Ray RLlib specifically, just to sort of really get a sense for how you would actually do this stuff. So again, this fits into this part of this pipeline where it's used both for training models. It needs a simulator of some kind or some environment that it can interact with. Usually that is going to be a simulator. And then it actually kind of fits into serving as well. Once you've trained your system, then you can actually apply it to try to do things in the real world, whatever that means for you. Oh, and there is actually a URL, rllib.io, will take you straight to the documentation for the library itself. You don't have to necessarily go through ray.io. Okay, and roughly speaking, there's sort of 4 layers in RLlib. At the bottom, you have Ray, the stuff that we were talking about earlier. Then there's some core abstractions for reinforcement learning that kind of understand the basic ideas of running epics, policy management, talking to a simulator, that kind of stuff. And on top of that is a very large library of standard algorithms. This is an area of hot research. The list that I'm going to show you is actually obsolete, but there's a lot of algorithms people have developed to optimize different aspects of training. Again, you're going to be running this thing over and over again, these epics, in order to train the system. So there's all kinds of ways in which you might want to optimize that, including using a cluster. And it's designed to be flexible enough that you can plug in your own custom algorithms, which you would do if you're a researcher or really an advanced user. And then I'll talk about the 4 blue ones here. Those are kind of interesting. OpenAIGM, that's that simulator library that's really popular for testing algorithms. And we'll see an example of that again in a minute. You can also have a scenario where you don't have just one agent, but maybe you have multiple agents, either as peers, working together, or maybe hierarchical, where lower level ones are focused on specific subtasks. The big one, sort of the parent agent, is kind of pulling it together for larger goals. Policy serving is about, okay, I've trained this thing. Now I want to actually use it in like my microservice environment to do whatever it is I need to do. And then offline data, this one is really interesting to me because it's an area that has not seen a lot of attention. But you recall a minute ago, I said that one of the big challenges for applying reinforcement learning to some major non-trivial applications or whatever is that often you need to write a really good simulator for them. And sometimes it's hard, maybe even not feasible for your budget or whatever reasons, to write a good simulator. The idea with offline data is, this model is, sometimes these systems actually have really good log data or telemetry data. And then we can actually use that as sort of a run or set of runs that happened in the past. And can we actually train a reinforcement model or system on that data rather than have it talk to a live simulator in some sense? So instead of being live or online, it's effectively offline. So again, this is an area where there hasn't been a whole lot of research done yet, but I think over time, as RL gets used in some much more sophisticated applications, this will be an important tool for people actually being able to use it. I see there's a couple of questions, so let me just quickly check that list if I can find my mouse. Okay, yeah, the first question is, Ray can be used with Python and other languages. Yeah, they've mostly focused on Python. It turns out there's actually a Java API for Ray that was written by the largest user of Ray, which is Ant Financial in China. The last time I looked at that library, it did the job. I found it's not very idiomatic Java at all, so it takes some getting used to. But if you actually want to try this with Java, you can actually use that API, and there's documentation on the Ray side about it. Someone's asked about this idea of updating the weights in the neural network. What does that mean as far as if you're doing it in a distributed way? You'd have to wait for all this computation to finish before going to the next step in the epic. Some of these algorithms are designed to make that work a little better, to basically train in parallel. They kind of like shard the data space, train, and then bring the results back. So there are ways people are trying to address this problem so that even though you're in a cluster, you're not blocked on this one giant neural network that's being trained, and hence, create some synchrony for you. Let's see, and the next question about, you wouldn't give a RL agent access to most the system while they're still training because, it could make poor decisions, and which could have really bad consequences, like if you're controlling a chemical plant. What about transfer learning? That's a really interesting question. So there is this idea, and this is used in a bunch of places outside of reinforcement learning as well, especially natural language processing. If you know anything about this space, that's where the big models are, where there are like billions of parameters and it costs, thousands or hundreds of thousands of dollars, even millions of dollars to train these models. They're so big. There's this idea that you train this model on some generic core corpus of information, whether it's documents or whatever. And then you can take that model and add a few more layers to the network and then train it, effectively treat it as like an early iteration of the model, and then keep training it with these additions so that you customize it for the particular domain that you're interested in. So that would solve this big problem of, some small company that wants to do NLP. I'll give you a specific example. Suppose you're an insurance company and you want to do natural language processing on like your claims forms, your transcripts from your customer service calls and all this stuff, where there's kind of a specialized vocabulary, but it is English, let's say. So you could start with a generic English model, like one of the really big ones that are out there, BERT and so forth. One way to do it, start with those generic models, add a couple of layers to the end and train with that as your basis, and then effectively customize this generic model to be more specifically trained for your purposes. That's a really good way of saving a lot of money, a lot of, let's face it, greenhouse gas emissions. But it also could apply here. What has not happened yet, at least to my knowledge, there hasn't been a lot of sort of generic models that have emerged in specific to reinforcement learning where this could be applied. However, I think where that's likely to happen first will be in things like autonomous vehicles and robotics, like the walking robot kind of things, where there's some just general things that are going to be common across a lot of different particular examples. So I do think that's a pretty interesting idea of sort of getting around this problem of training. But I should say, though, going back to the question, you still have this issue of you need something to train against that's reasonably representative of your world. And even if you start with a generic but already trained model, you'd have to decide, is it likely to cause my chemical plant to explode if I try doing training with it? Chances are you're going to have to find some balance between writing a simulator to take you farther to the ideal model, while figuring out when you can actually trust it in a real scenario. And finally, a question about TensorFlow versus Ray distributed training. So what we'll actually see is we're going to use TensorFlow in a very simple example as the underlying neural network for the policy training. And in fact, Ray is designed to be very flexible. And also this hyperparameter tuning thing I mentioned is designed to let you plug in any of these deep learning and other systems that you want to use. It'd be kind of crazy for Ray to re-implement those. But you can use kind of any of those that you want, or something even simpler like a linear regression if you want. And they also support integration with GPUs. I don't know about TPUs yet, but I imagine that's available now as well. And it is designed to be a cluster system, so multiple machines is kind of out of the box, even with the very basic Ray API that I showed you. So all of these things are options and are widely used. Okay, so I'll go back to the slides now. Let's see, I can't see my mouse, so I kind of have to guess where it is. Give me a second. Well, let's see if I can just go. There we go. Okay, so here's an eye chart with a bunch of the APIs that are already, algorithms that are already bundled into Ray. I'm not going to go through all these because most of them wouldn't make a lot of sense. I will mention that some of the ones on the lower left are sort of classic algorithms: actor-critic, deep Q networks, and proximal policy optimization is one that I'll actually use without going into a lot of details. This is one that's designed for a cluster-wide training regime where I'm going to have like a central coordinator. I'm going to spawn out work to Ray workers somewhere in the cluster or on my single machine, and then aggregate the results back when I'm done. So without going into a lot of detail because of time's sake, there's a lot of different, most of these things are designed to support different optimization strategies or different particular problem domains. I should mention in passing too that this is actually available inside SageMaker. So if you're already using SageMaker, you can use Ray. And I think this is an old slide, but I believe it's also fully available now in Azure as well. Finally, one of the reasons that Ray is so generic and fine-grained is because when you think about the problems of reinforcement learning from the point of view of how am I going to implement this as a compute problem, there's actually a wide range of challenges that you have to solve because there's a lot of different components here that each has very different kind of compute requirements. So if you've ever written any sort of game engines or anything like that, you're familiar with some of the ways that you might structure fine-grained interactions and state management in a simulator like this. The agent probably has similar kind of requirements that could be coarse-grained or very fine-grained, could require a cluster even if they're very, very big and complicated. Neural networks, there's like a whole lore that's emerged about training these things where it's a little bit more in the old MapReduce paradigm in a way, although it's much more iterative than typical MapReduce. But nevertheless, it's more about like big data movement and efficient coordination among processes. And then you're going to be running this over and over again. So you'd like this to be as efficient as possible. And you'd also like to work in tools that help you make smart choices when you're trying different parameters for this network on the right. Like, how many of these layers should I have? How big should they be? You know, is it 32 or 16 or whatever? Those kind of questions. That's where RayTune is pretty nice. It has a bunch of algorithms built in that people have developed for making smart decisions about when to just stop training something because it's not going to be very good, but instead focusing on things that seem to work better. Someone asked also here if Ray supports the ability to train on different memory size GPUs. What if the model doesn't fit in single GPU memory? I'm not actually sure about the answer to that one. I think that there's work that's been done to support that, but this is one of those areas where, as I showed Ray earlier, it's designed to be very simple for doing simple things, but sometimes you need to reach in and do some very fine-grained, tuning and configuration, and it's getting better about that. There's a lot of configuration options when you're getting into RLlib, for example. I don't know specifically about this one. I haven't had to deal with that myself. Okay. This is sort of a vanity slide that basically says that RLlib has comparable performance to hand-tuned and handwritten algorithms. So they've done a pretty good job optimizing the internals. Like most high-performance Python systems, it's actually C++ under the hood. When I was at Anyscale, there was actually a discussion of should we convert it to Rust, but we kind of decided not to go that route. Nevertheless, we use C++ for the heavy lifting. That's they. Okay, let me actually do a demo here. And I'll show you a little bit about the tutorial stuff. So what I'm going to do is go to this window. And let's see, I guess I got all the questions. So first of all, here's that. If you want to get these slides or a longer version of them, ignore the URL. This is where it redirects to. If you just go deanwampler.com/talks, you'll end up on this page, and you can find the ones that have this sort of blurry picture, which I like to use because it was an accident. The shutter was too slow, but I actually thought it came out cool. So anyway, you can find this talk, at least a longer version of it there. This is what the Ray page looks like. And in particular, if you want to find out about training, like they have some online training videos and they did periodic training, you can find out about the community for Ray. You can get to the documentation. Like if I go to, let's see, here's the RLlib one. Does this work actually? There it is. Okay. Here's the documentation for RLlib if you're interested. And that's another good place to start rather than just use the tutorials. These are some of the canned videos that are available if you want to, follow along at home. But basically what you're going to be working through is this suite of notebooks that I helped start create when I was there. I'll have this link at the end of the slides as well, but it's basically github.com/anyscale/academy. And it also has instructions for setting this up so you can run it locally on your laptop. I think they also offer this on their hosted service as well. Once you set all that up and start Jupyter running, then you end up with something that looks like this. And what I've done is I've actually opened some of the notebooks. And in fact, if I go to this slide, let's go to the top here. So anyway, there's overview notebooks and so forth. So you can kind of navigate to what you're interested in. There's tutorials in RayTune. We're going to focus on RLlib. There's stuff on just basic Ray if you want to learn more details about how to run Ray in your environment. But anyway, so let's go through this. What I'm going to do, I think, did I want to use this one? Actually, I'm going to skip that one. So here is an example of, actually the simplest way to run RLlib is actually to run these command line tools that come with Ray rather than use the API I show you some examples here of using the API if you prefer writing in Python. But what we're actually going to do is run some of these commands to train this neural network. If you've never worked with notebooks before, it's kind of cool that you can use like bang and then a regular shell command, and this will shell out and create it. So what I'm going to do here is I'm going to run this proximal policy optimization algorithm. I mentioned that a minute ago. It handles things like distributing work over a cluster. I'm going to train a model. I'm going to use cartpole as an example. And let's see, I was going to actually, why don't I show you the video for that first? You know what I'm talking about. So cartpole is kind of the hello world of reinforcement learning. I basically have this cart that goes back and forth in one axis, and I have this vertical pole that it's trying to balance. And so the trick here is I want to train this thing to balance the pole for some long period of time. The maximum score I can get is like 50 ticks. I think there's something like that. The number's 50. I'm not exactly, or sorry, 500. I'm not exactly sure what it corresponds to. It's not really seconds. But if it keeps going, if it stays balanced for, up to a score of 500, then you effectively won. And when you start, it's just going to fall over because it has no idea how to balance this thing. It actually learns pretty quickly. I think this took about a minute. So what I'm going to do is not run the command. I'll just finish describing it and then show you sort of this output so that we can cut right to the chase and actually see it in action. But so anyway, I'm going to use this PPO algorithm. I could pick a number of them. Cartpole version 1, and they start at 0, so it's actually the second version. This is in that OpenAI gym environment where I have that like Running Man thing that I showed you a little clip for. This is the one everyone starts with when they're first learning. I'll show you another example in just a minute that's a little bit more fun and advanced. Usually you want to give it some stopping criteria, and it could be, if you get within, if you reach a certain score on average. And the thing is, you usually focus on the average score because sometimes it'll do really well by accident. Other times it'll do really poorly. And it's kind of the average where you want that to be as high as possible so that most of the time you have a good run when you actually deploy this thing. But what we'll do is we'll just train for 20 iterations. It turns out that's actually plenty for getting a very good result. We'll also save our model every 10 iterations so that this is good for two things. One is that if it crashes, I can just pick up where I left off. But also when I actually run, I'll be able to just point at a checkpoint and have it run with that saved information. And then we'll also checkpoint it at the end when we're finished running after 20 cycles. So if I scroll back to the top here, what you would start to see is just these sort of status messages coming out. And then notice what you see over here. I need to move this little box here with the video things. Yeah, and then I think this is okay. So what we want to do is get the average reward to go up, like I said, to about 500. And when it starts, it's really stupid, doesn't know what it's doing. It only lasts like 4 seconds, and then it falls over with a reward of like 22. But as we go, notice that the reward is going to get bigger and bigger. Sometimes it might go down a little bit, but mostly it's trending up. And it doesn't take very long before it's in the 400s. And as we get to the bottom, it's gotten almost to 500. In fact, most of the max, it always hits 500 during this training run, at least a few times. Sometimes it doesn't do that great, but on average, it gets very close to 500, and it can stay up for like over a minute that way. So that's what you would see if you were watching this train. And again, because it takes several minutes, I won't actually do it again. I ran this earlier so that I can just show you what it looks like. The other thing you can do if you've worked with like TensorFlow or some of these other systems, there's this system called TensorBoard that you can use to look at parameters. And let me make sure I have the selection here right. I'll come back to that in a second. So this is what TensorBoard would show me about the training runs and the parameters that were developed, how it was doing as it ran. This can be useful for like debugging problems, seeing the results of your work later. It's just the integration is built into Ray. TensorBoard is something that Google mostly manages. This is actually the Ray dashboard. So when I'm running, I can actually see how many of these workers are running. It's basically like 2 per CPU core, roughly speaking. So that's why I have like 8 or something. Maybe it's a little more than that. And it shows me how much RAM I'm using. Plasma is like the in-memory cache where it keeps results. When I've done those like Ray add arrays stuff, that's where it's going to be caching the results that I can then fetch. And then it obviously needs some disk space as well for like flushing things. And I've had this up for a little while. Has it really been 24 days? No, I think this is a mistake. But anyway, what I'm going to do is I'll show you this little video quickly. This is like one epic. So what you can see what it looks like when it runs, but let's actually run it for real. So I have this little shell script that's bundled with this thing that basically calls that RLlib command again, but this time to actually run it. It's called rollout when you're actually applying this trained model, and I'll let it run for 5 episodes. So let me run this one. And what you'll see in a moment is it's going to pop up a dialog where it's actually going to show the thing operating. And then I'll just show one more quick video of another model and then go to the slides and wrap up. So it's actually loading the checkpoint that was last saved when that's this thing right here, when I did the training earlier today. And it takes a moment for there it is. So now it's actually running 5 episodes where it tries to keep this thing alive. It actually gets all the way, and it's not going to fall over, basically. You'll see it suddenly jump, and that's when it's actually going to the next episode. But, the 20 took like 5 minutes or something to train, a small neural network, 2 layers. I didn't show the parameters, but this is actually a very simple problem to solve with reinforcement learning. And you can basically see what it's doing. So I'll just close this and show you one that's a little bit more fun. Unfortunately, I think there's a bug in the notebook, and that's this one. This is actually training a bipedal walker. And the idea is that I want this thing to actually do bipedal motion. This is another OpenAI gym simulator. The cool thing is this one you have to train for maybe a half an hour because it's a much more sophisticated problem and it needs a bigger neural network. But notice how it actually learns to walk. I think this is pretty neat. So it doesn't actually do bipedal motion. It does this sort of weird shuffle with one leg in front of the other. If I let it train for a day or maybe a few hours, it would probably get to the point where it actually figures out that it's more efficient to put one leg in front of the other, alternating. But once again, what it shows you is if you start with something naive, it often comes up with a solution that works, but it's actually kind of really bizarre from what we're used to thinking of. And that's the so-called bipedal walker. Okay, let me go back to the slides just to wrap up quickly. And then we'll be done, and I'll take the last questions. Okay, so just to recap, reinforcement learning is about training an agent to maximize the cumulative reward while it interacts with an environment, and it usually requires lots of runs to train it. Oops, I hit the wrong key. And RLlib is a really nice but very high-performant library for doing this kind of stuff, which I recommend checking out. And I'll leave this, I'll go out of presentation mode, but anyway, here's the links. If you want to get to the Academy on GitHub, find my longer talk that's here, or send me email or whatever. So let me go to the last questions here. Is there any noise modeled in the simulations? That's a really interesting question because there is some evidence that noise often makes these systems in general, even not just reinforcement learning, more effective, more robust against like overtraining and so forth. I'm not actually aware of how people have studied this particular idea in the context of reinforcement learning, though.
Dean, were those rays that were coming out of the robot, for lack of a better word, in the last slide, were those line casts or something else that was trying to detect the ground?
Yeah, that little tiny ray, I think that's a sensor. It's representing a sensor for the terrain. I believe that's what that is. Someone asked, does RL generalize well? It does. It's kind of subject to the same sort of issues that neural networks can be. But because you're training over and over again, it actually is pretty good at sort of optimizing away some of the fragility that you might have in other kinds of models. So it all ultimately comes down to the quality of the simulator often. Someone asked about other books. There isn't a whole lot of books out there. There are a few that are less expensive. but I've mostly found it just more interesting to go to some of these websites or online tutorials that people have published about RL rather than rely on books, other than the Sutton and Bartow book.
Do you think with all those different areas where RL can be used, particularly with advertising, media, and finance, is there a danger that they'll absorb the attention?
It's quite possible. I think that it's still at the research stage to some degree. So you need organizations with a lot of ability to experiment now, like Netflix and YouTube. But I think they'll develop some strategies that become more generally useful. And I suspect that because this is one of those areas where the best model usually wins, that you'll see a lot of people adopt this, especially if it gets to the point where it's actually more efficient than doing the classical algorithms.
Okay, great. So I think we're pretty much almost out of time. So Mark, can you talk about our upcoming webinars?
Sure. January 19th, we will have a speaker arranged. You'll hear about it soon. But just in case, if any of you in the audience feel like I'd really like to give a talk, this is the time to let us know. Not only January 19th, but we have several other months this year that we're looking for speakers. So Brant Devinder, I saw this video on the Pacific Northwest National Laboratory, which is like Argonne. There's off in Seattle. I found this speaker on how to build a quantum computer. And now he's a physicist, but this was a really fascinating talk. Great speaker. You won't want to miss this. So that's on February 16th next year, just in 2 months.
All right, great. Thank you very much. Also as well, here's our YouTube channel, so you can see our previous talks, and the talk from Dean will be there shortly. And also, I mean, we're a volunteer organization, so we would like more people to help us with the ACM Chicago. So we are looking for people who have skills in writing, planning, videography, audio, and editing for our videos, especially when we go back into person, and also networking with future speakers and topics. And it's a really great way to connect with the community and to use your talents for that. And also, like what Mark said too as well, we're looking for future speakers. So if you have a particular topic that you want to talk about, please let us know, and we can put you on the agenda for next year. All right, so we're pretty much out of time. So I'd like to thank Dean. Thank you very much for your wonderful presentation. The slides and the recording of the video will be provided afterwards, as long as the PDH certificate, if you need one for your PDH hours. And also as well, that's pretty much about it. Thank you very much all for attending. This is our last webinar of this year. So happy holidays, Merry Christmas, Happy New Year, and continue staying healthy and safe. And we'll see each other in the new year. So thank you.